Alrighty, in this video, we are going to be talking about the fundamental theorem of calculus. So if we have a function, and that's denoted by little f, if that's continuous on the closed interval a to b, and big F is the antiderivative of f on the interval a to b, then we have the integral of a to b of little f of x, and that's going to be equal to the antiderivative of f of b minus the antiderivative of f of a. So we have our function. We're going to take the antiderivative of it, and then we're going to see what big F of b is and what big F of a is, and then we're going to subtract it. So looking at number 9, we have the integral from 1 to 2 of x squared minus 3. I'm going to take the antiderivative of x squared minus 3. That's going to be 1/3 x cubed minus 3x. And then we have my limits of integration being 1 to 2. I'm going to evaluate my limits of integration at my upper limit of 2 first, since that's my b value. And then I'm going to evaluate my lower limit, which is my a value. Going to clean this up a little bit. So 1/3 times 2 to the third, that's 8/3 minus 6, and then 1/3 minus 3. Clean this up some more, so that's going to be 7/3, and then -6 minus -3 is minus 3. Clean this up even more, you're going to get -2/3. All right, number 10, I have a coefficient of 3 that I'm going to take out. So I have 3 times the integral of 1 to 4 of the square root of x dx. I'm also going to rewrite the square root of x so that it is an exponential form. So I have 3 times the integral from 1 to 4 of x to the 1/2. And what I'm going to do is take the antiderivative of x to the 1/2. So if I were to do that, I'm going to up my power by 1 and then take the reciprocal of that and multiply it. You'll notice that the 3's will eventually cancel out, so I have now 2x to the 3/2 using my limits of integration of 1 to 4. All right, so with my limits of integration being 1 to 4, I'm going to substitute and evaluate at my upper limit of 4 first, and then my lower limit of 1. So I have 2 times 4 to the 3/2 minus 2 times 1 to the 3/2. The square root of 4 is going to be 2, since 2 is in the denominator here. And then since this is 2, 2 to the 3rd power is 8. 8 times 2 is 16, so this is 16. 1 to any power is basically 1, so this is essentially minus 2. And then you're going to get 14. Number 11, we have my limits of integration being 0 to pi, and then we have sine x dx. So if I were to take the antiderivative there, that's going to be negative cosine x, and then my limits being 0 to pi. So now I have negative cosine of pi minus negative cosine of 0. I'm going to clean this up a little bit, and instead of negative, I'm just going to say positive. So I have negative cosine of pi plus cosine of 0. Cosine of pi is -1, and then cosine of 0 is 1. Negative is a positive, so +1 plus +1 is a +2. All right, on to number 12, we have the integral from 0 to 2 of 2 times the absolute value of x minus 1. I'm going to take my coefficient out first so that I have this right here. And here's my problem now for number 12 and eventually for number 13. We have the absolute value of x minus 1. We don't have any tips or tricks or rules to help us with the absolute value of x minus 1. I cannot get rid of the absolute value and then take the antiderivative of x minus 1, can't really do that yet. So what I'm going to do is visually graph the absolute value of x minus 1, take the area, and then call it a day. Now, because we are using the fundamental theorem of calculus, I am going to be using FTOC, meaning that even though I am, graphing this, and you could take the area, this is just going to be good practice in terms of today's lesson. And then at the end, we could verify that our area is what it seems. We have two areas. We have this area from 0 to 1, and then we have this area from 1 to 2. Which means I'm going to break up my integral into two parts. I have 0 to 1. But notice how from 0 to 1, I have this area, and that line is not x minus 1. So thinking about math 3, remember that our definition of a piecewise function is negative x for x is less than 0 and x for x is greater than 0 for your parent function. The same process is going to happen here where we have negative x minus 1 or negative x plus 1, which kind of makes sense because this is going to be 1 right here. So for your left area, you're going to have negative x plus 1 dx. Your right area, well, that's still going to be x minus 1. Okay, so I'm going to take the integral, aka the antiderivative of both left and right. So I have negative 2, negative 1/2 x squared plus x from 0 to 1, plus 1/2 x squared minus x from 1 to 2. And then we're going to just call it a day and then hope for the best. Using the fundamental theorem of algebra, I have negative 1/2, 1 squared plus 1. And then, because I have a lower limit of 0, and if I were to plug in 0 and 0 here, that's just going to be 0. So I'm just going to leave it like that for my lower limit of 0. Going to evaluate to my upper limit of 2 for my second term. So that's going to be 1/2, 2 squared minus 2. And then my lower limit of 1 is 1/2, 1 squared minus 1. Then we are going to simplify all of this. So we have 2. Negative 1/2 times 1 squared is just negative 1/2 plus 1. And that's going to be 1/2. So that's 1/2. Then we have 1/2 times 2 squared. 2 squared is 4. 4 divided by 2 is 2. 2 minus 2 is 0. So that really doesn't do anything much. And then we have 1/2 times 1 squared, which is 1/2, minus 1, which is negative 1/2. Oops, this should be a minus using my fundamental theorem of calculus, since this is my second term. So this should be negative 1/2, which becomes a positive 1/2, which then we get 2 times 1, or an area of 2, using fundamental theorem of calculus. Now, obviously that was kind of long. Like I said a couple minutes ago, that was just good practice. What we're going to do now is actually take the area using geometry and using triangles, because obviously that's going to be the easiest in terms of number 12 and 13. So, if I were to evaluate 2, And of course, we're going to have a 2 right here, so that's going to stick out. This triangle right here is going to be 1/2, our base being 1, and then our height also being 1. Plus 1/2, height being 1, not height, base being 1, and then height also being 1. So we have 1/2 plus 1/2, or 1, and then 1 times 2, because we took out the coefficient of 2, will give us 2. And notice how that only took us less than a minute to do instead of this thing right here. However, you will be expected to probably do something using the fundamental theorem of calculus in terms of these problems. So let's say 9, 10, and 11. Whereas for 12 and 13, it's probably better if you guys were to just use geometry. And for 13, I am going, yeah, that's not, okay. For 13, I am going to be using geometry just because this was definitely a mess. Okay, so what we're going to do here is think about my zeros of 3x minus 4, and that's going to be 4/3. So here, if I were to graph this, I'm going to have 4/3 right here, and then we have 0, and then we have 5 somewhere right here. I'm just estimating on what this looks like. We have 4/3 right here. Okay, so if I were to evaluate 0 for this function right here, I'm going to get 3 times 0 minus 4. So this is going to be 4. And then at 5 right here, I have 3 times 5, which is 15, minus 4, which is 11. So this right here is going to be 11. So if I were to do that, I'm going to have 1/2, our base being 4/3, and then my height being 4 for my triangle on the left. And then my triangle on the right here, I'm going to have 1/2. I'm going to have my base. And if I were to make that in terms of 3 so that it's easier for me, that's going to be 15 over 3. So this would be 11 over 3. So that's my base. And then my height being 11. Okay. So this, I'm going to take out a 1/2. And honestly, I'm going to take out a 1/3. So that means that I'm left with 4 times 4 plus 11 times 11. So that's going to give me 1/6. 16 plus 121, which is 137 over 6. Now, the reason why I took out a 1/3 is because I had a 3 in my denominator here and a 3 in my denominator here. So that means that I'm left with 4 and 4 on the left, and then 11 and 11 on the right. Then simplify that to get 137 over 6. If you were to do it using the fundamental theorem of calculus, it's going to get a little bit wonky. So whenever you are getting problems like this, use geometry. Don't use calculus. I think geometry will be the easiest in terms of absolute value. All right, so on class, we are going to do more practice on the fundamental theorem of calculus and properties of definite integrals.